we're going to be looking at the section of chemical equilibrium, but specifically the Kc calculation. I have just started recording, so we're all good. All right, so when we look at the Kc calculation, Kc is basically called your equilibrium constant. And if you ever go to study university level chemistry, you'll discover that you actually get a whole bunch of Ks. You get a K, well, you guys have already encountered Kw. Kw is the dissociation constant for water. When you go to university, you'll discover there's a Ksp for how much things dissolve, which is your solubility product. There's, I'm just trying to think of all the different Ks. Let's just go, there are a lot of Ks. I think there's also a K for pressure and partial pressures of gases. But the point is you get a lot of different K values. They're all equilibrium constants, but they're for different things. Kc, the C stands for concentration. Okay, so we are specifically dealing here with the equilibrium constant for concentration. You're not going to deal with situations where you don't have it's capital K, uppercase K, lowercase c. You're never going to be dealing with any of the other ones other than your Kw, but that we'll discuss under acids and bases at a later stage, okay, when we do acids and bases. So some schools, and you're going to notice I'm not writing this down, my hands are up right now, not touching the board. Some schools teach this as your equilibrium constant basically represents the ratio of your products divided by your starting materials. You'll notice I'm not bothering to write this down because it's the one thing that we will not give you any marks for in an exam. So if you write it down in an exam, no marks. However, in my head, that's how I think of it. So I think that if the Kc is large, we've made lots of products and we've got more products than starting materials. Okay? Please note it exists when we're in equilibrium, which means we're still having a rate of forward and reverse reaction being equal to each other. So the starting materials are turning into products at the same rate as the products are turning back into starting materials. But it's saying if we've got a large Kc, most of our starting materials have turned into products before we reach the situation where they're exchanging or going from starting materials to products and products back to starting materials at the same rate. Now, fortunately with Kc, we can kind of ignore that aspect and we'll only look at it later when we're asking, is it a large or a small Kc? Does the Kc get bigger or smaller? Now, I'm about to start with what confuses a lot of people. So just bear with me, breathe in and out. I promise I will get to answering this question or the questions about this later. So please can I ask that until I've finished going through this little bit here, you don't ask questions in between, okay? At the end, if I haven't answered your question, the end of the little bit that I'm doing now, then I'll happily get to it. So imagine that we have a reaction where A moles of A, don't freak out, plus B moles of B is in equilibrium with C moles of C plus D moles of D. Very confusing looking. Basically, your A, B, C, and D are what we call your stoichiometric coefficients or your mole ratios. I'll do an example just now to explain to you which each thing is. It's not letting me choose there. Your capital A, capital B, capital C, and capital D are all the identities of the substances. So, for example, I could have, and I'll use the same example I used last time, nitrogen plus hydrogen going to make ammonia. Now, in this particular reaction, it's one nitrogen reacts with 3 hydrogens to produce 2 ammonias. So in this case, this would be considered little a, that would be the 1. Big A would be the nitrogen. Little b would be the 3. Big B would be the hydrogen. And then we don't have a C and a D. We've only got one product. So we could almost imagine that this would then become little c and this would become big C. If we ended up with a situation where we had more than 2 starting materials, then we just keep going with the imagined idea, okay? So that just explains to you what this layout looks like. To calculate our value of Kc, our Kc is always going to be equal to the concentration. Remember, square brackets from the lesson on Tuesday. Square brackets means concentration. So it's going to be concentration of our products first. So it's going to be concentration of capital C to the power of C multiplied by concentration of D to the power of D over, so products, remember I told you that Kc was concentration of products, don't write it down, over the concentration of the reactants, but it's written as A to the power of A times by B to the power of little b. So this is the rule that they often teach you. Now, unfortunately, in an exam, if you don't replace the A's, the B's, the C's with things that are relevant to the specific example you get, nobody cares that you know that, okay? But it's actually a lot easier to do than writing the theory. So this is a little bit like maths equations where we put in X's and Y's and variables and we come up with general rules and then you can plug things into a formula. This is kind of like our formula, but it isn't always the formula because we may have more than just two things on the top and we have more than just two things on the bottom. In this case, we're going to quickly work out what the Kc is, or the Kc expression is. So the Kc expression for the Haber process says that the Kc will equal. Now, it's always going to be your products first, so this will be the concentration of ammonia to the power of whatever's in front of it, which is 2. Since I've got nothing else, I don't put anything else. If I had 4 other products, I would put every one of them multiplied afterwards here, raised to the power of its own stoichiometric coefficients. So whatever's there raised to the power of whatever's in front of it. Once we've done all of the products, the things that are after the equilibrium arrow, we go back to the ones that are before. Those go in the denominator, because remember, this is in sneaky writing, and I don't ever want you to write this down. Concentration of our products over our reactants. I'm very tempted to not leave that on the board because I can tell you right now it's where a lot of students go wrong. They think that's their formula, concentration of products over reactants, and it isn't. This is the formula that you're going to get the marks for. All right, so I need to take away that times because there wasn't anything to times by. Over here, our starting materials are nitrogen to the power of 1. If you really want to, you can write in a 1, but you don't have to, over the concentration of hydrogen to the power of 3. Okay, and that is how you work out the expression for Kc. Please note, there is usually in any question involving this, 1 mark allocated just for you being able to look at the balanced equation and write down that expression. Later, you'll need to plug things into it. Sometimes you plug from the front direction, which means you may have to work it out. You're not given it directly, but you may plug in those concentrations to calculate Kc. But I must be honest, in looking for questions to prepare for tonight's lessons, I actually discovered that I had to go all the way back to 2015 before I could find a question where your focus was to calculate Kc. In all of the questions they've been giving lately, they give you Kc, and you need to work out something about one of the concentrations, either the mass that gave you the concentration or something like that. They're not straightforward. Most of the questions on Kc are between about 7 and 10 marks. Okay, most of them are 8 or 9 marks. So it's a big chunk of the marks in your exam paper. In fact, straight out, if I say your average is 8, divided by 150 times 100, this little thing that we're doing today is about 5%, a little bit over 5%. That makes quite a big difference to your overall mark if you can get it. The good news is, because they're marks for specific things, even if you mess up on one little point somewhere, as long as you follow the rest of the steps, you can easily get 5 marks out of 8 just for doing the steps, even if you do them slightly incorrectly or with wrong values. All right, so before we go any further with this idea, I'm going to put up an example, similar where I write down an equation, and I'm going to ask all of you, please, to work out the Kc value for me. Now, there's one last thing that I didn't mention yet. I probably should put it in before I make you do it. It's very important that we only, well, not only, that we leave out, leave out's probably the right term. We always leave out any solids. Okay, so if I were told these here are gases, so we include them. We can include all gases and we can include all aqueous solutions, but we leave out solids and we leave out liquids. Now, liquids is a problem in terms of our terms. When I'm talking about a liquid, I'm not talking about salt water as a liquid because it's runny. I'm talking about H2O is a liquid because it's pure. The only way that you get a pure liquid is if there's nothing else in it. So anything that's dissolved in water, we say is aqueous, we don't call it a liquid. And we can also get things to be liquids by literally melting them. So mercury, Hg, is usually a liquid at room temperature because it's already melted, okay? Sometimes ethanol, which is your, I just got to get this right, C2H5OH, your ethanol can be viewed as being a liquid if it's only got ethanol in it. Now, realistically, as a chemist, you don't get pure ethanol. Ethanol gets to about 99%, and then there's a little bit of water in it always. We're prepared to round up that little bit of water. You can get pure methylate, pure methanol, so CH3OH could be pure, but the only way that you really know that it's pure is if it's got an L after it in the formula, or if it's got, I don't know, sulfur solid. An L or an S after it in the formula, you just leave it out of here completely, all right? That means that instead of that number, we usually say put in a 1. Just the number 1, and that 1 usually will disappear itself. All right. Can I ask everyone to quickly take a screenshot before I clear everything off? Okay. So the question that I'm going to ask you is a tricky one, but it's a realistic one. So I'm going to tell you that calcium carbonate can decompose in equilibrium to form calcium oxide. This is a horrible, sneaky one. And carbon dioxide. Okay? I'm warning you already, this is a sneaky one. Listen to what I just said. So, first of all, our mole ratios or stoichiometric coefficients are a 1, and a 1. Ta-da! Okay? So I want to give everybody just a quick second before I give you the answer to write down what you think the Kc value will be. If you're wrong, it's okay. This is where we learn. Okay, can I ask that as soon as you have done that, you just quickly indicate to me that you're done with a thumbs up if you think you've got it. Okay, good. All right. Now, I'm willing to bet that some of you are a little bit scared to do it, but fortunately, I'm not going to ask you to give me the answer. It's fine if you don't feel like it. We can just jump straight in. So, first of all, I go to the product side. Remember, products go on the top, but we don't write products on the top. Just leave it, okay? We've got calcium oxide, but I'm not going to write in calcium oxide because it is a solid, so I just write the number 1. If you want, you can leave it blank, and that's fine too, because you know that there's going to be a 1 there. But if nothing else comes on the top, you must put a 1 at least initially. Then I move on to the next bit, which is carbon dioxide. It's a gas, so I can write square brackets CO2. Happy with that? Okay. And it's to the power of 1, which you can write in for now, but we're going to simplify just now. Then we go over starting materials, but be careful. That is a solid. So we just put in a 1. Believe it or not, the equilibrium constant for this particular decomposition, it's called a decomposition because calcium carbonate, one substance, breaks down into calcium oxide and carbon dioxide when it's heated. In fact, this is a part of how we make cement. We take calcium carbonate and we heat it to make quicklime or what we use in cement. So over here, the 1s cancel, the top disappears. And basically, we can say here that the equilibrium constant is just equal to the concentration of carbon dioxide. Now, something that I didn't really focus on, but we'll get to just now, is we're talking about equilibrium constants, which means that when we're talking about this concentration, it is only going to be the concentration at equilibrium. Okay, it can't just be the concentration at any point. If you go to university, they actually specify that Kc is only equal, or these two are only equal to each other when we're in equilibrium, and they actually give the expression, which was your c to the power of c times by d to the power of d over a to the power of a and b to the power of b. They call that the expression of mass action. They've got other names for it as well, but we can get away with just pretending that none of that exists, and it all works. Okay. Quick show of hands, who got that one correct? Okay, good. I see a couple of you. Yay, that's fantastic. Well done. All right, please can I suggest that you don't raise hands unless you've got a question. Raising hands is for questions and thumbs up is for giving a response. It just makes it easier. So if I see a hand raised, then I assume that there's a question. Okay, cool. And a lot of you say you did. All right, so please note, capital K, this C is a subscript because as it is, it's an equilibrium constant of concentration. A little bit like you'd write Kp is energy due to potential. So potential energy. Here, the subscript C is to indicate that it's concentration. One more example before we move on to actually practicing this. What about if I have hydrogen gas reacting with iodine gas to produce 2HI gas? Can I ask everybody once again, just quickly give it a go, see if you can work out your Kc value. I know you can see me writing. I'm not going to keep putting it all in. I'm just putting my preventions in place. Okay, good. When you've got it, give me a thumbs up. Okay, I can see a few thumbs up. That's wonderful. All right, and because I don't want to take forever, I'm going to start jumping into this. So remember, it's always going to be products on top. So here it's going to be HI to the power of 2 over H2 to the power of 1, because there's a 1 there, times by I2 to the power of 1. Now, having marked this question for the last 2 years, I have seen every version of nonsense that people can put in here. I don't even think I need to go into what they do because I'm not going to give you silly ideas for your own exam. But the one that I've found that people mess up the most is that they invert it. So they put those on top and those at the bottom. The second thing that people forget to do is they forget to raise it to the power. So they just have HI and they don't square it. And the last thing that also drives us up the wall is instead of timesing and multiplying these together, they suddenly come up with little pluses that come out of nowhere. So please remember, everything is multiplied and that is what it looks like. All right, before I go any further, can I quickly just check that everybody gets the basic idea as to how to formulate that particular calculation, how to work it out. Now, any exam question that you get, there's 1 mark for that. So even if you look at the question and it gives you heart palpitations, at that point, stop, breathe in and out, write out your Kc, and then look at the next thing. Even if you can't do anything further, you've got 1 mark that's been guaranteed that's then in the bag. All right. So I'm going to quickly clear this. I think everybody's got it. So let's just quickly clear it. The next thing that comes in is how do we do this? So I'm going to teach you now quickly how to do what we call an ICE table. Now, I know I do this differently to some teachers. Please, you're welcome to do it the way you've been taught if you've already been taught it. The way that I'm going to teach you is going to always be marked correctly. And basically what I do is some schools separate out certain columns and I merge them into one. So I'm going to go back and I'm going to use the example I just did, which is hydrogen reacting with iodine in equilibrium to produce hydrogen iodide. Now, quite often in an exam, this is an imaginary table that I'm going to make up here, they give you, or this is if they're really nice, they give you a nice setup where they start off with initially so many moles of this is put into a container, and then at equilibrium so many moles are left over, or this amount of concentration is left over. You have to fill in certain blanks, and then you plug everything into the equation. So I do the following columns, and you're not always going to have all of these. You may skip one, or you may not need one depending on what information you're given. So I usually work on the idea of I, C, E. Some people talk about rice, where they do R as the first column, where R is the ratio. I don't put in ratio in its own column. I basically, when I write it out, I write it with the numbers in the balanced equation, and that gives me my ratio, so I know to look here for the ratio. I don't believe it needs its own special column or its own special row. I'm quite happy to include it there. So the ratio column tells us the ratio of the different substances in the balanced equation. Very important. I stands for initial. This is how much of everything we initially have in the container before we establish equilibrium. C stands for change. Now, some schools separate this out into a made column and a used column or something like that. I don't see the point. The substance is either going to be made or it's going to be used up. It can't be made and used up at the same time. Raman, is there a question? Okay, please come back if there is. And the E stands for equilibrium. I, in fact, don't usually use equilibrium in that form. I often use the following symbol for equilibrium personally. More than equilibrium. It looks like an E, so you can kind of get away with it. And then these often can start off with being number of moles. So more often than not, you're going to have a number of moles initial, number of moles change, number of moles equilibrium. And then right at the end, because we need to plug things into the equation, you will have the concentration at equilibrium, which you'll notice I like to do with the equilibrium sign like that. Concentration at equilibrium. All right. So looking at this column that I've set up, Cameron, is there a question? Please, if there is, just make sure that you do ask it, because I will happily answer any questions. This table, by the way, does not need to be drawn perfectly, but the official memo that we mark by, this is the easiest way for you to guarantee you get your marks. Unfortunately, maybe you're not going to like me for this. This is not going to be the question you get asked. But if you can't do these easy guys, you're not going to cope on the harder ones. We start on a really easy one, which is how you put everything in. Then we'll deal with the, oh my gosh, if they give us everything backwards, what do we do question. So usually they will give you the following information. They may not give you the number of moles initial. They may give you the mass or the volume or something else like that. But using all of the things that you know from stoichiometry, you can work out the number of moles. So if I tell you the mass of hydrogen, you turn it into moles and you plug it in. So let's say, for example, that I start with 10 moles of hydrogen and 8 moles of iodine. Okay, so this is what they'll tell you. They'll tell you that the volume of the container is whatever. I usually 2 decimeters cubed. That seems to be a common one. And I have this habit from years at school where my volume is top right-hand corner of my page. The second I read it, I plug it there. I can't even tell you why, but it's just that I read it, I plug it there, and then I know where to look. So you'll see there's my volume. And then they'll say something strange, like at equilibrium, it's discovered that there are 2 moles of iodine in the container, and your question is to calculate Kc. Now, once again, I'm going to repeat, this is your dream question. This is not what they're going to give you, but if you can't do this, you're stuck. So this is how I fill in this particular table. First of all, there are a couple of gaps that you can fill really easily. The initial number of moles of hydrogen iodide can be assumed to be 0. If we're making it, we don't start with it. I don't start baking cakes by having cakes. They're the thing I make. So it's very rare that you will ever start with any product in your container. So you can usually assume, and they won't tell you this, they'll just say initially those are put into the container, and you'll know, well, if they didn't put in any hydrogen iodide, it's not there. Okay? So that's the first thing that you can fill in for yourself. The next thing is using our change column. If I started with 8 moles and I finish with 2 moles, I must have used 6 moles. Now, please note, if you do not put in a negative here, we are not sympathetic. If we cannot see by what you've done everywhere that that was meant to be a negative, you will lose marks. So it's always a good idea to clearly make sure that everybody understands that is a negative. Okay? Then the only column here that ever has to be in the mole ratio of 1 to 1 to 2 is your change column. Your initial never has to be in the correct mole ratio. You could have just coined stuff in. Doesn't have to be in the right ratio. Your equilibrium also doesn't have to be in the correct mole ratio, because remember, if you just randomly put stuff in the beginning, you're going to have stuff that didn't react. Excess reagents means that they're not going to be in the perfect ratio. But this middle change column has to be, which means that I can assume that these will be 1 to 1 to 2, which means that if I used 6 moles of I2, I used 6 moles of H2, and I made 12 moles of HI. The reason these two are negative is that they're my starting materials. If these two are used up, this one is made. Now, there are some very rare occasions where they're, instead of having the forward reaction favored from where you start, where you actually start with your product and you use the reverse reaction. Then all that would happen was this would be negative and those two would be positive. But the rule here with regards to signs is that all of your starting materials must have one sign, and all of your products must have the opposite sign, and all of them must be in the correct mole ratio. Talking about where we give you marks, there is 1 mark given for you having them in the correct ratio. Even if these are completely nonsense values, if it's in a ratio of 1 to 1 to 2, and they've got the right signs, you get a mark. Okay? Guaranteed freebie mark, doesn't matter what anything else says. Then the next mark that you're going to get is for your subtraction. So we had 8 moles here, we used 6, and we were left with 2. We started with 10 moles here, we used 6, and we were left with 4 moles. Okay? We started with 0 moles, we made 12, and we end up with 12 moles. If you do this minus this equals this minus this equals this, and this plus this equals this, there is a mark here for your summing. Okay? Even if one of your answers is complete nonsense and you got the wrong thing in the wrong place, if I can clearly see that from your initial through your change, it equals the bottom, and these have the correct sign. So it must be 10 minus 6 gives me 4. You can't have 10 plus 6 gives you, so this can't be a plus and this and this. Two of them must, or this one of the starting materials or products must subtract and the other side must add. Okay, so you've got to have that. You can't have 10 plus 6 gives you 16, 8 plus 6 gives you 14, and 0 plus 12 gives you 12. One has to go in the opposite direction. Then the last step is, how do we get from moles to concentration? You do not need to show that concentration is number of moles over volume. You don't actually need that formula, although it's what we're using. What you do need to do is take this value and divide it by your volume. So if I have got 4 here, divided by 2 gives me 2. You don't have to put all your units in here. Just for the record, I'm putting all of the units in. You don't need these. 2 moles per decimeter cubed, 1 mole per decimeter cubed. And this is 12 divided by 2 is 6 moles per decimeter cubed. If you've got that where I can see the correct division, okay, which effectively is us using the equation concentration is number of moles over volume, you get the next mark. All right, so that is effectively 3 marks that you can have in the bag before you do anything else. Okay. Then we move on to what you've got to do next to calculate Kc. Now, it's very important. Kc is temperature specific, which means that whenever they give you the value of Kc, they'll say, at 450 degrees Celsius, the Kc value is this. I ignore the temperature, okay? Later, I'll look if they give me another temperature, if it's bigger or smaller, but that actual temperature doesn't matter. It's not going to affect anything that you do. It's just important that you understand that the equilibrium constant depends on what temperature it's at, which is why they always give you that information. That number doesn't go anywhere. You ignore it. So now what we're going to do is we're going to put in that expression for Kc that we worked out earlier. Kc is equal to the concentration of Hi squared divided by the concentration of H2 times by the concentration of I2. There's your next mark. And then there is a lovely mark for substitution. This means that if I take the values I've got here, even if they're wrong, and plug them into the right places here and square them where I need to and don't when I don't, I get another mark. So here, if I put in 6 squared over 2 times 1, even if I can't do maths, I get another mark, okay? But if you leave off your squared, you don't. Sometimes they get really fussy, and they actually say that if you leave off or if you get this formula here wrong, even if you do everything underneath it correct, you don't get the mark. So just be careful. If this bit here is wrong, or if this bit here has round brackets, don't do the round brackets. If it has round brackets instead of square brackets, and they've got to be properly square, you don't get the marks further on. They can penalize you and take off all of those marks. So please be very careful. All right? You'll get lots of things where you got more than one product. All that you'll do is you'll put it in as well. I've got examples that I'm going to do later where we'll have that situation. Okay, so this is just one specific thing. When we substitute into Kc, do the numbers need to be in square brackets? No, but at this stage here, they need to be in square brackets. And once you sub them in their numbers, they can be in anything. So here it's going to be 6 squared divided by 2 divided by 1 gives me an answer of Kc, which is 18. Please note that your Kc value is regarded as being unitless, so you do not put any units on it. All right, I'm quickly going to answer questions. So ma'am, can you please clarify why the temperature will not affect the equation? Temperature is a factor that affects it. Yes, the temperature will affect what the value of Kc is, okay? But it's not going to affect what you plug in anyway. So if I told you, okay, so let's just quickly ask, did I tell you what temperature this reaction was being done at? I never told you. It could have been 250 degrees. In fact, I'm not even going to give a value because there is actually a specific, with this particular reaction, there is a recorded formal value that it should be. So any value that I give you here, I'd be totally making up. But that temperature, if I told you it happened at 200 degrees Celsius or however many Kelvin, you didn't plug that 200 in anyway. So it will affect what the values you get here are, okay? But it won't affect how you treat this, okay? So you wouldn't have done this any differently if I'd instead told you that the number was 500 degrees Celsius. Okay, so that's what I mean by it doesn't affect what you do. Yes, it can later be used to tell us if a reaction is endothermic or exothermic, because if we change the temperature, we can see how the Kc value itself changes. All right, so let's just quickly see. Please, can I re-explain why it's 0 in the corner? Because when you start the reaction, you don't have any product. If I'm going to be making hydrogen iodide, I don't put in any hydrogen iodide to begin with. That would be a little bit counterproductive. So usually you can assume, unless they tell you otherwise, because they can, that you don't start with any product. All right, so this is a very basic introduction into how this works. We can hope that this is what you'll be given, but it isn't always going to be the case. All right, so what we'd be doing in other questions, and you'll see it's pretty much the same thing, but we would instead start with the Kc, and then we'd be working backwards to work out what the initial number of moles of hydrogen is, or what the initial mass of hydrogen is. So we can sometimes work backwards. In fact, not sometimes, we usually work backwards. All right, so I'm going to clear all of my drawings here. I'm going to quickly stop sharing. I'm going to go across to the question that I've got us ready to do now, and then I'm going to start sharing again. Okay. Okay, so this question comes from a really old past paper. As I said, I think I had to go back to 2015 or before I got it. I can't tell you which paper it is. Okay, so Cameron, how is KC useful in chemistry and what does it mean? Please, I'm going to write this down, and I've already told you 10 times I don't want you to do it, but KC, okay, I'm not going to write it down. KC tells us the ratio of starting materials to products. So it effectively tells us how much of our starting materials got converted into products. The rule is if you have a large value of KC, it tells you that you have more products than starting materials. You can't say that it tells you that the forward reaction is favored, because if you're in equilibrium, the forward and the reverse reaction are favored. But it can tell you that when that reaction happened, most of the starting material rushed and turned into product. Okay. If you have a small value of Kc, then it means that very little product was formed. Just give me a second. Okay, so that very little product is formed and that most reactants remained as reactants. Yes, some turned into products and then they turned back into reactants and we set up an equilibrium, but most of them remained as reactants. As a rule, if you want to make a large amount of product, you would want a large KC. So in industry, a large KC is a good thing. Also, it's very difficult to identify where small and large come in. I did see a university level thing where they actually gave a number, but I generally regard a large KC as being bigger than 1. Bigger than 1 means more product is made than or your concentration of products is higher than your concentration of reactants. But quite often it ends up going into tens and hundreds and thousands. The small KC means that very little of the starting material turned into products and most of it just sat there and didn't do anything. If you consider that your value of Kw is 1 times 10 to the negative 14, that means that 1 in every 1 times 10 to the negative 14 water molecules split up to give you hydronium and hydroxide ions. So very little of the water broke down, most of it just remained as H2O. Okay, just a reminder, this comes from the rule that H2O liquid goes to OH minus plus H3O plus. Effectively, your Kw there, in fact, maybe this makes a bit more sense here. This is a liquid, so it becomes 1. So it'll become the concentration of OH minus times by the concentration of H3O plus, both to the power of 1. So that's where your Kw comes in. It's water. In fact, it's 2 waters decomposing into hydroxide and hydronium. But all that it says is that very little of it is actually reacting. All right. Okay, so with regards to, I've just had a note here saying on Siavula, they teach that a Kc value less than 1 is a shift to the left and a shift to the right. I don't really review it as being a shift to the left or right, but you can, I guess, use those terminology if you really want. I usually talk about shifts when equilibriums have been disturbed, or that an equilibrium forward reaction, you can't even say is favored because once again, they've got to happen at the same rate. So it's just that a large Kc usually indicates a high yield and a small Kc indicates a low yield. Recently, these are the kinds of terminologies that they've been trying to get people to use. All right, I need to get into this so that we can actually get this question done for today. So the question here says, and I hope everybody can see this, I'll zoom in if I need to, but I think it's big enough. An unknown gas X2, which means immediately that they can make up any Kc value they want because nobody can go and look it up and then contradict them, is placed in a sealed container. If you remember from Tuesday, we said the container had to be sealed in order for us to establish an equilibrium. And we are allowed to form X3 at 300 degrees Celsius. Once again, that 300 degrees Celsius is to tell us what temperature it is, but we don't use it for anything. So the reaction reaches equilibrium according to the following balanced equation. So there it is. First question, and this isn't on KC, but I'm covering it as revision from Tuesday. How will the rate of formation of X3 compare to the rate of formation of X2 at equilibrium? Write down only higher than, lower than, or equal to. Oof, I'm suddenly wondering about this question. Now, the reason I'm going to tell you I'm wondering about it is if the question was just the rate of reaction, rate of forward to rate of reverse, there'd be no doubt that the answer should be equal to, okay? Because the rate of forward reaction equals the rate of reverse reaction. However, there's a tiny part of my brain that's looking at this right now and saying that there's 3 moles and there's 2 moles. So we're effectively going to make 3 moles of that for every, 2 moles of that for every 3 moles that we decompose. But I don't think I'm going to pay attention to that part of my brain. And I'm going to go, because this is just a 1-mark answer, with the fact that they are equal to. We're just going to assume that we're talking about rates of reaction. Flat, leave it there. Okay, so the rates of reaction will be equal to because they're in equilibrium. Okay, now what I wanted to discuss with you, sorry for bringing in a minefield that I suddenly looked at and wondered about. If I need to correct it myself later, I'll get back to you. But I'm pretty certain that that one, they wouldn't have wanted you to overanalyze it. So we're going to move on to question 6.1. No, 6 there. It says, the reaction mixture is analyzed at regular time intervals and the results obtained are shown in the table below. So we go at 0, 2, 4, 6, 8, and 10 seconds, and we see the concentrations there. Then it says, calculate the equilibrium constant for this reaction at 300 degrees Celsius. Now, there was a reason that I chose to make us do this specific question, is it's actually a really easy one. Can I quickly ask, and I'm going to pause sharing, who thinks they could already do this? Just looking at the information that's on your screen. Okay, good. 2 of you, 3, 4, 5, 6, 7. Okay, so it looks like a large number of you think you could already do it. That's wonderful. So you're starting to see what they're asking. Now, because we've got a limited amount of time and I don't want to leave anyone behind, I'm going to ruin the surprise. Those of you that already know it, by all means, get going on it. The first thing that you need to do is you need to figure out what concentrations you're going to use at equilibrium. Now, for those of you who are confused and don't know where to start by working out Kc. Here's an equation. Let's jump straight in and say, well, Kc will equal, it will equal the concentration of X3 to the power of 2 over the concentration of X2 to the power of 3. Yay, 1 mark, done. Then we need to go and ask ourselves, which values are we going to sub in? Now, they're really nice. You didn't have to do your initial, your change, your final. You just plug it straight in here. We've got a question. When do we reach equilibrium? And if you remember from the lesson on Tuesday, I said that we reach equilibrium when the concentrations remain the same. So the rate of the forward and reverse reactions are equal to each other. And because of that, the concentration of our starting materials and our products don't go up and they don't go down. They stay the same. So if you look here, X2 gets smaller, smaller, smaller. And at time of 6 seconds, it stops changing. From 6 seconds to 10 seconds, nothing changes, which means that these here are our equilibrium concentrations. So then we jump straight away to putting them in. So over here, remember your square brackets was for your Kc. You can plug in normal round brackets afterwards. 0.226 to the power of 2 divided by 0.06 to the power of 3. Okay, and then you plug it into your calculator and hope that you get an answer or a question this easy in an exam. Okay, can't say it'll never happen because this did come from a past exam paper, and provided my calculator is right, which I think it is, this answer is 236.46, which is a nice neat number. All right. Now, because I want us to get into the habit of answering exam type questions, I'm going to answer the next 2 questions as well before we jump onto another different version of Kc. The question says more X3 is now added to the container. So we are effectively going to be increasing the concentration of X3. Please note, it's a gas. Very important that you check that. If it was a solid, it wouldn't make a difference. Okay? The question was, how will this change? The change is the increase in the concentration of X3. Remember, concentration is square brackets. How will this change affect the amount of X2? Write down only increases, decreases, or remains the same. Okay, so we are disturbing the equilibrium. Okay, so I'm going to write out a full solution because it does say underneath, use Le Chatelier's principle to explain your answer. So I would go and say here about, according to Le Chatelier's principle, please don't abbreviate Le Chatelier's principle in exam, the disturbance is an increase in the concentration of X3. Therefore, the system will act to decrease the concentration of X3. In order to decrease the concentration of X3, therefore the reverse reaction is favored. And if the reverse reaction is favored, we will make more X2. And therefore more X2 is produced. Please remember, when they ask about the amount of X2, you can assume that that means the number of moles. Okay, so more X2 is produced. So going back to the first question, my answer here is going to be that it increases. Now, I've got a scary bit of information for some of you. Do you know that if you don't put in this answer here, if you leave it blank, you will get no marks for the explanation? Okay, so as of how the exams were marked last year, if you do not put in an answer, it doesn't matter how right your explanation is, you don't get the marks. It used to be a case that if you left off the answer, you could still get the marks, and it was only if you put in the wrong answer, that we'd ignore your subsequent. This is what we call negative marking. So if this answer is wrong, we don't mind what you've written here, we don't read it, we cross it out. Okay, no marks. But they've changed it recently when we were marking to if you leave off an answer, you also can't get any marks. So please, please, please don't forget to commit to an answer. I know that it used to be a case of you could get away and hopefully get more marks because you could get marks for your logic even if you weren't sure which way it went. But here you've got to make sure that you do this properly. All right. Can I quickly ask, has everybody copied down what they felt they needed from here? Okay, I'm going to quickly clear here and I'm going to move down to the next part of the question that I wanted to give you. Okay, so that was the one question, sorry, and here's the next question. Now, this question here is the type that you're most likely to get in an exam, which is why we're quickly going to focus in on it. Okay, sorry, I'm jumping around here. I'm going to have to move this bit up so that everybody can see it. So I hope everybody can see this. I may even just move the question down a bit. There we go. That makes me happier. All right, so this question here comes from a past paper. And I felt that it's very similar to what you should get. Jordan, do you have a question? Okay. All right. So this question is the last question I think we're going to get to in the last 10 minutes. I don't know if we're necessarily going to get to all 10 in the last 10 minutes, but it's what I aim to do. Yes, what's the question? Hello? I heard a man.
Sorry, ma'am. Back to that question. Yes, ma'am. Can you hear me?
Yes, I can, but I can't go backwards. So just quickly ask your question and I'll try and remember.
Yeah, it was about the Le Chatelier's principle.
Yes.
I don't get why is it therefore the forward reaction, the reverse reaction is favored.
Okay, the reverse reaction is favored because we want to use up the product. Since the disturbance was an increase in the concentration of product, according to Le Chatelier's principle, our solution or our system will act to remove that disturbance by decreasing the concentration. The way that you decrease it is to use it up, and the reaction which uses it up is the reverse reaction, because then it becomes the starting material of the reverse reaction, and its concentration decreases while the original starting material's concentration increases. All right. We did cover this in the lesson on Tuesday. Can I ask, just because I need to get to this last one in the last few minutes, if you don't still understand, stay behind at the end and I'll go through it then, okay? All right. Okay, let's quickly get going here. So you're told that hydrogen and iodine are sealed in a 2 decimeter cube container. So I immediately start by writing my volume, top right-hand corner of my page. The reaction is allowed to reach equilibrium at 700 Kelvin. That's a token value. You take a mental note, say maybe it's higher or lower, look for it later, but ignore it otherwise, according to the following balanced equation. Question 6.1, give a reason why changes in pressure will have no effect on the equilibrium position. This is one of those things that we looked at in Tuesday's lesson. Does anyone have an answer? Is anyone brave enough to give one? I'm sure there's someone who knows it. Okay, I'm going to be nice. Pressure, if you remember, is determined by the number of moles of gas. Yes, Tasneem. Was that an offer?
I was going to say that.
Yeah, what were you going to say?
I was going to say that pressure will have no effect on the position because the number of moles of gas, it's 2 on the side and 2 on that side. So
good.
There's no...
Because there is an equal number of moles of gas in the starting materials or products or on both sides, anything like that. Okay, so because we have got 2 moles of gas here, 1 there and 1 there, and 2 moles of gas there, it's equal on both sides. So increasing the pressure will make both rates of reaction go up, but it won't favor the forward or the reverse. I did see that somebody typed in something about the temperature. Please note the question wasn't anything about Kc value itself. There would be a disturbance if we changed the pressure, okay? So you can only talk about the Kc value changing if the question is about the Kc value changing, not just if we want the equilibrium to stay in equilibrium. That isn't part of it. Okay, so the next question says, at equilibrium, 0.028 moles of hydrogen and 0.017 moles of iodine are present in the container. That's at equilibrium. Calculate the initial mass of iodine in grams that was sealed in the container, sealed for us to establish equilibrium, if the Kc for this reaction is 55.3. I did see that there was a question. Okay, don't stress. And I'm going to start through this. We've only got about 6 minutes. So if everybody doesn't mind, I'm going to encourage you to go and practice on Siavula after this. So go and do all of the practice you want to. But for now, I'm just making sure that everybody has a video to watch on how to solve a problem like this. So you could start at either end here, okay? You may start by working out Kc and then plug in things later, or you may start by setting up your table. So I'm going to do both at the same time alongside each other, just because I feel like it. So I'm going to have H2 plus I2 goes to give me 2HI. Once again, my ratio's in there. Then please, you don't even have to put in these dividing lines, but it sometimes helps. I have been given the number of moles at equilibrium. So I've got my number of moles initial, my number of moles change, my number of moles equilibrium. You remember I like that symbol. And then my concentration at equilibrium. I always find that I set up my table and I always put in, like you guys have got lined paper, so you'll obviously use the lines on your paper and ideally put in a little bit of ruling lines. It doesn't have to be a neat table. It doesn't have to have edges. That's more than fine. So we are told that at equilibrium, we have 0.028 moles of hydrogen and 0.017 moles of iodine are present in the container. Okay, so I'm going to start by using my volume here. This is just what I'm doing. You can do these in any order, it's allowed. So I'm going to say 0.028 divided by 2. I'm going from there to there. Remember, C is equal to N over V, so I'm taking my number of moles and dividing by my volume. So I get 0.014, and I'm taking this and dividing by 2, so 0.017, just checking I've got all the values written down correctly, yes, divided by 2 gives me, oh, this is a nasty number, so I'm going to make it 8.5 times 10 to the negative 3. I'm not thinking further than that. All right, that's where I stop. Done, finished, not playing anymore there. I'll come back to it just now. Then what I'm going to do is I'm going to set up my expression for KC. KC in this case, and it's one we've done a few times today, is HI squared over concentration of H2 times by I2. Now we know that the value of KC is given as 55.3. You're going to laugh, but do you know that there's a mark for that? There's a mark for this bit here, where you put everything in the right place. And there's a mark for subbing the value of KC into the right place. So even if you can't do anything else, write up that equation, stick the KC in, and then make it look like you're going to put something in later, because you can't just get a mark for that if you haven't kind of put in a little bit more. So here we're going to have the concentration of HI, which we don't yet know squared, over the concentration of H2 is our 0.014. This value here is the concentration of hydrogen at equilibrium, so we plug it in there. The concentration of iodine is 8.5 times 10 to the negative 3. And from this, we can work out the concentration of HI squared. Please be very careful. This is where most people mess up with their maths. So just be aware of it. So HI squared is going to be this times this times this. So I'm going to quickly work that out on my calculator without doing an extra step to mess it up and hoping that I get it right. I get an answer of 6.5. It's very small. 5807 times 10 to the negative 3. Please speak up if I've messed up there. Can't see anything that I've done wrong. And then I square root that answer. And that gives me that the concentration of HI is equal to 0.0811 moles per decimeter cubed. Everybody happy with that? Please note, here there is a mark for this side, there is a mark for substitution in there, and there usually will not be a mark for this value, but there may be a mark for using it later. We usually don't give marks for answers en route, we give marks for how you use those answers. So this is going to go in here as 0.08. Please, I'm going to use 0.0811, but if you use 0.08, nobody's going to mind. Then what I needed to do is this got divided by 2, and this got divided by 2. This value, to get it up to here, must be multiplied by 2. There is one mark for divide by 2, and multiplied by 2, but please, you've got to get it that way round. If you make up an answer, put it in here, and then divide it by 2 to later fill in that, we don't give you the marks. We actually have to check that it's divide, bottom answer times, and not just you getting a random value here that came from nowhere and then dividing it by 2. So if I times this up by 2, I get 0.1622. Now, the question, if we go back to it, asked us for the initial mass of iodine. Please note, if we're looking for the initial mass, they're actually hinting that we need to get the moles first and then to go backwards to work out the mass later. So from over here, I have to use the assumption that I started with no moles. Always a safe assumption. You start with things, you put them into a container. Hydrogen and iodine are sealed in the container. We didn't put in some hydrogen iodide. There was nothing, which means that if we started with nothing and we finished with that number of moles, we must have made 0.1622 moles. Now, believe it or not, we do not care about what happens with hydrogen here. If you fill in the values, fantastic, but they didn't ask you anything about hydrogen. What we care about here in order to be able to answer the question is how many moles of iodine here we had. This change column, remember, is the one that is in mole ratio. So it's 2 parts to 1 part. So if I take that and I divide it by 2, I get that I must have used 0,0811, okay? Which means that over here, I must have started with something, used that to get to that. Please bear in mind, if you go backwards, you actually have to add it back. So I'm going to take this value and add that positive value. So 0.017, I get that I must have started with 0,09812. And I keep all of my decimal places because I don't want to lose anything. So that is the number of moles of iodine that I started with. I just quickly need to go and get my molar mass. I think iodine's 127. Yep, it is, but I'm not going to look silly and get it wrong. Okay, so over here, what I'm then going to do is I'm going to say that the number of moles is the sample mass over the molar mass. Can everybody still see my question? Just quickly give me a thumbs up if you can see it. Can everybody see the question? Okay, cool. Sorry, it just disappeared off my page. So, all right, good. I just had to check with everybody. The values that we've got here, or we're looking for the mass. The number of moles is 0,09812. If you'd rounded it up at any point, as long as you didn't round to less than 2 decimal places, you're fine. Over 127 means that the mass, the initial mass, I'll explain the minimum just now. This one wasn't minimum. So it's going to be this times 127 gets me to the point that the mass must be 12.46 grams. Okay. Now, sometimes if this question, instead of being done with iodine, which was a gas, is done with a solid. So imagine this was a solid here instead. You could still do all of the same steps. Instead of just saying calculate the initial mass of whatever, they'd say calculate the minimum initial mass. Because you've got to remember that if this is a solid, it doesn't go into your KC calculation at all, which means that we could actually have had more of that present and it wouldn't affect our answer. So it's just something to note that if you ever are asking this exact question, the substance that you're asked about is a solid, it wouldn't have gone into your KC expression, and therefore because of that they usually say what is the minimum amount, because the minimum amount is the smallest amount that would have allowed us to have enough moles for everything else to happen. All right, I saw that there was a question there. Why is, oh flip, you're right, sorry, thank you for correcting me. Iodine is diatomic. I'm going to blame the late night. So therefore this should be twice as big. Yay, thank you for picking that up before I stopped recording. It's always good. So the mass here is 24,92 grams. Thank you. I always like it when you guys correct it before the video goes out and people learn the wrong thing. All right. Can I ask any other questions? Any other issues with this particular working out? All right. So I'm going to quickly stop sharing. Please don't disappear just yet. Okay. Can I quickly ask who has a better understanding of KC calculations because of what we've just gone through? Okay. All right, that looks like almost everybody, which is fantastic. All right. Oh, wait, I don't want to do that. Okay, so I'm just going to quickly stop recording and